up, everyone, because we're diving into some seriously mind-bending stuff today. You know how you sent in that question about AI having those aha moments, those flashes of insight that we humans experience? Well, this article, Do Machine Learning Models Memorize or Generalize? Hmm. Takes us right to the edge of that mystery with this whole grokking phenomena.
Yeah, grokking, it's like, when you stare at a joke for ages and then suddenly it clicks and you get it. That's kind of what we're talking about here, but with AI.
So instead of a bad dad joke, it's like suddenly understanding the laws of physics or something.
Well, maybe not quite at that level, but it's definitely a big leap in understanding for these AI models.
Okay, so we're talking about training these models on tons of data, hoping they learn to make accurate predictions. But how do we know if they're really understanding the underlying patterns or just becoming masters of memorization?
That's the million-dollar question, right? It's like the difference between a student who aces a test by memorizing the textbook versus one who actually grasps the concepts. One's just regurgitating information, while the other can apply their knowledge in new and interesting ways.
So in AI terms, memorization would be like overfitting the data, right? The model
Yeah.
gets really good at predicting the training data, but throws something new at it and it falls apart.
Exactly. And that's where generalization comes in. It's the hallmark of true learning, both for humans and AI. A model that can generalize can take what it's learned from one set of data and apply it to a completely different but related situation.
And this article suggests that sometimes, instead of this gradual learning process, these AI models have these sudden jumps in performance, these aha moments where they certainly grok the problem. It's almost like watching a kid try to ride a bike for the first time. They wobble around, fall a few times, and then boom, something clicks and they're off.
And the thing is, when you look at the data, at the graphs of the model's performance over time, it really is this dramatic shift. You'll see this flat line, this period of stagnation, where it seems like the model's not making any progress, and then all of a sudden, it shoots up, almost vertically. It's pretty wild.
Okay, now I'm picturing some Hollywood AI suddenly becoming self-aware and taking over the world. But I'm guessing it's a bit more nuanced than that, right?
Let's not jump to sentient AI just yet. While this grokking phenomenon is definitely unexpected and intriguing, we don't want to get carried away with anthropomorphizing these models. It's not like they're suddenly waking up and becoming conscious, at least not that we know of.
Okay, good to know. So how do researchers even begin to study something like grokking in a controlled way? I mean, are they just throwing complex problems at these AI models and hoping for the best?
Well, to get a handle on what's happening, researchers often start with simplified tasks, sort of like giving the AI the equivalent of puzzles to solve. One example is modular addition.
Modular addition. That doesn't sound very simple.
It's actually more straightforward than it sounds. Think of it like adding hours on a clock face.
Okay, like if it's 10 o'clock and you add 4 hours, you don't get 14 o'clock, you get 2 o'clock.
Exactly. You circle back around, and it turns out that even with this relatively simple task, some AI models display this grokking behavior. They'll struggle for a while, seeming to just memorize the answers, and then bam, they figure out this clock math, and their performance jumps dramatically.
So it's like they suddenly understand the concept of a cycle, of things repeating in a pattern.
Yeah.
Fascinating. But how do we know that's what's happening inside the AI's brain?
That's the real mystery, isn't it? And to get closer to an answer, let's look at another task researchers use to study grokking, one that gives us a bit more of a visual clue about what might be going on. Imagine a string of ones and zeros, like binary code.
Got it, like the Matrix or something.
Yeah.
What's the AI supposed to do with this binary string?
The task is to figure out if there's an odd number of ones within the first three digits of the string.
Sounds easy enough, but I'm guessing there's a catch.
Of course. To make it more challenging, they also throw in some extra digits after those first three, just random noise that's irrelevant to the task.
So it's like trying to listen to a specific conversation in a crowded room. There's all this extra information that could distract the AI from the important bits.
Precisely. And what's interesting is that during the early stages of training, the AI seems to be doing just that, trying to make sense of the entire string, noise, and all. It's like it's trying to memorize every single possible combination of ones and zeros.
So brute force memorization instead of actually understanding the pattern. But then how does it suddenly switch from that to grokking the solution?
That's where things get really cool. Researchers can actually visualize the AI's attention during this process using something called heat maps.
Wait, we can see what the AI is focusing on. Tell me more about these heat maps. How do they work? Okay, so heat maps, like a thermal image, but instead of showing heat, it shows what the AI is focusing on.
That's a great way to put it. Imagine you're reading a textbook and you use a highlighter to mark the most important sentences. These heat maps are kind of like that. They show which parts of the data, in this case, the string of ones and zeros, the AI is giving the most weight to when it's making its predictions.
So as the AI is learning, those heat maps are changing. What do they look like when it groks the pattern?
Here's the amazing part. As the AI starts to grok the solution, as it shifts from rote memorization to understanding, you can actually see the irrelevant digits, those extra ones and zeros, literally fade from the heat map.
No way. It's like the AI is training itself to ignore the distractions and zero in on the crucial information of those first three digits. That's wild. But how does it learn to do that?
That's the big question, right? One theory revolves around this concept called weight decay.
Weight decay. Okay, you're going to have to break that one down for me. It sounds more like something you'd encounter in the gym, not in the world of AI.
It's not as complicated as it sounds. Basically, you can think of the AI's thinking process as being guided by a bunch of knobs and levers. These are its weights, and each weight influences how the AI interprets the information it's given. Weight decay essentially adds a little nudge, a little pressure to those knobs and levers, pushing them towards zero.
So it's like encouraging the AI to find the simplest, most elegant solution possible. Don't overthink it. Find the most straightforward explanation.
You got it. And what researchers have found is that this pressure to simplify, this weight decay, seems to play a key role in triggering that grokking moment, that sudden shift from memorization to true understanding.
So it's like the AI is being pulled in two directions at once. On the one hand, it wants to get the answer right, to make accurate predictions based on the data it's seen. But on the other hand, it also wants to keep its thinking as streamlined as possible.
And sometimes it's in that struggle for simplicity that the aha moment
It's
occurs.
like suddenly it sees a connection it didn't see before, a more elegant way to solve the problem. That's fascinating.
It really is. Okay, now remember that modular addition task we talked about earlier, the clock math? Well, remember how we were just talking about the AI's attention focusing on those crucial first three digits in the string of ones and zeros? Well, it turns out something visually similar happens with the modular addition task. But instead of digits, the AI is focusing on specific points on a circle.
Okay, now you've piqued my curiosity. We're talking about circles now. I need you to walk me through this because I think we're about to cross into some serious, mind-blowing territory.
Imagine each number on a clock face has a corresponding point on a circle, right? So instead of just adding the numbers like we normally do, the AI starts representing those numbers as points on this circle.
Okay, I'm visualizing a proc face with dots for each number. I'm with you so far.
And here's where it gets really interesting. The AI, through the training process, figures out how to arrange these points on the circle so that it can perform modular addition just by rotating those points around the circle.
Hold on, I need a second to picture this. So the AI is basically reinventing the wheel, but instead of a wheel, it's this circular representation of numbers.
You got it. And it's not just any random placement of points either. The way the AI arranges them, the distances between them, the angles they form, all of these geometric properties actually encode the rules of modular addition. It's like the AI has stumbled upon this hidden geometric structure within the numbers themselves.
So the AI isn't just solving the problem, it's revealing something fundamental about the nature of math itself. That's incredible.
I know, right? It's as if the AI is saying, hey, humans, you've been doing math this way for centuries, but check out this cool pattern I found. It's a whole new way to think about it.
You mentioned earlier that initially those points on the circle, they seem random, but then as the AI trains, they suddenly click into this meaningful pattern. It's like, what did I say before? Like stars forming a constellation.
That's a great analogy. At first, when researchers visualize those points, it looks like just noise, static on a TV screen. But then, as the AI trains, guided by that weight decay principle, those points start to cluster together in very specific ways, ways that directly correspond to the underlying mathematical structure of modular addition.
It's like the AI is refining its understanding, going from this blurry, static-filled image to a crystal clear picture.
That's amazing. I can definitely see why researchers are so excited about this whole grokking thing. It's not just about building smarter AI, it's about the potential for using AI to unlock entirely new ways of understanding the world around us.
Exactly. And that's where things get really interesting and potentially a little unnerving.
Okay, so we've established that grokking is potentially really cool, but also a little spooky. But how do we get from here to, AI that can actually help us understand the universe better?
Well, that's the million-dollar question, isn't it? One very promising avenue is something called mechanistic interpretability.
Mechanistic interpretability. Okay, I'm going to need you to unpack that one for me. It sounds a little intimidating. It's not as complicated as it sounds. Essentially, it's about trying to reverse engineer the AI's brain to understand its thought process. We want to know not just what the AI is thinking, but how it's thinking.
So less about reading the AI's mind, more about understanding its operating system.
Exactly. We want to break down the AI's decision-making process into its individual steps, see how the different components interact, and ultimately figure out what leads to that grokking moment.
So if we can create AI that can reliably grok, that could change everything, right?
Yeah.
From scientific discovery to medicine to maybe even understanding ourselves better.
The possibilities are pretty mind-boggling when you think about it. Imagine AI that can not only solve incredibly complex problems, but also explain its reasoning in a way that we humans can actually understand.
It's like having an AI partner in discovery, pushing the boundaries of knowledge alongside us. But what if we never quite figure it out? What if this grokking phenomenon remains a mystery, even as AI gets more and more sophisticated?
That's certainly a possibility, and it's one we need to be mindful of. But even if we don't achieve perfect understanding, the pursuit itself is incredibly valuable.
I think that's a good point to end on. Even if we don't have all the answers yet, this exploration of grokking is pushing us to ask some fundamental questions about the nature of intelligence, about learning, about what it means to truly understand something. And those are questions worth pondering, whether you're an AI researcher or just someone who's curious about the future of technology and our place in it. So until next time, keep those questions coming and keep exploring the ever-evolving world of AI.